Okay, well, thank you so much for the introduction. So, well, it's a very pleasure and honor to me to visit here, this UNIST for the first time. And also, I'd like to thank Professor Seong for hospitality. Let's see, so today I'm going to talk about the topic of Quiver Yangians and Donaldson-Thomas invariants. And this is, in a sense, a complicated topic encompassing various different areas of mathematics and physics, ranging from geometry to algebra to representation theory, and but also supersymmetric gauge series and string theory. But on the other hand, some aspect is purely combinatorial, which is not might look complicated, but there is some in principle very something down to earth. What I'm going to talk about is based on series of works I did with Wei Li and Dima Garakov in a series of papers. If you want a short summary, there is a very short summary of several pages, which I have here. And many of the things I say is based on my earlier works when I was a PhD student and master student listed here, partly with Hiroshi Oguri and some other collaborators. So let me begin with some overview of what I'm going to talk about. As in the title, we are going to talk about the Donaldson-Thomas invariants. So these are the invariants of the Calabi manifold. So there are numbers, specific numbers coming out. In fact, a set of numbers, and it's defined on three-dimensional geometry, toric Calabi threefold, with toric, which says we basically say there is a sufficient torus action. 3 copies of torus action. And given this geometry, you can consider some moduli space. It's quite often in mathematics you consider the moduli space. And in moduli space, in this case, is the moduli space of sheaves. So these are like a vector bundles, if you like, some fancy version of vector bundles. And then you don't count all the bundles, but so-called stable ones. In mathematics, they are often we encounter in various different situations such a moduli space of counting stable objects. Very, very general pattern. Now, this itself is a moduli space, and the moduli space itself can be complicated. But now there is a torus action coming from toric Calabi-Yau. So the geometry on the geometry there is a torus action, and somehow related with that, the torus action is inherited in this moduli space. So there is a torus action on the moduli space itself, in addition to the geometry. And in this situation, there is a formalism of so-called equivalent localization, which says that instead of considering the full space, you can just consider the fixed point set of the moduli space under this action. And hence, you get some final set of, well in general, infinite, but the discrete set of points. You're going to get the discrete set of points, and that's where the combinatorial structure emerges. And it turns out that combinatorial structure, I'm going to call the crystal melting. There are several different incarnations. For example, it might be formulated as a Daimer model, counting perfect matchings, for example. So some combinatorics appear. And that combinatorics itself is pure combinatorics and just a set of combinatorial structures satisfy some axioms. And the origin of this is that there is an underlying algebra. So there is an infinite dimensional algebra, which we introduced, and we call the Quiver Yangian. It's an infinite dimensional algebra, and you can consider representation theory. And when you do the representation theory, you can consider the weight space of the representation. Or in other words, when you do the representation, you represent the algebra as some set of matrices, essentially, acting on some space. And that space is represented by this combinatorics of crystal melting. So in fact, this Quiver Yangian, the infinite dimensional algebra, explains why you might want to discuss such combinatorial structures. And as the name suggests, that this Quiver Yangian is determined from the data of the quiver. Well, actually more like a quiver with potential, or in physics language, superpotential. And in fact, from this viewpoint, you can recover the original Donaldson-Thomas invariants by considering the character of the representation. If there's a representation, there's a concept of character, and then that will reproduce the generating function of Donaldson-Thomas invariant. So you can go back and forth. This is a geometry in a sense. This is the combinatorics part, and this is algebra. So this is a relation interplay between geometry and algebra and representation theory. And all of these are motivated by the physics of supersymmetric gauge series. That's what I'm going to discuss. And I can be, my discussion today is divided to 4 parts, roughly speaking. Well, I'm going to discuss first the geometry part of what Donaldson-Thomas invariants are. This part is a little bit geometrical, so could be a little bit technical, but it's okay. And then I'm going to introduce the quivers, and then quiver itself, and then the algebra part, Quiver Yangian, and then I'm going to discuss the representation theory part of the story. So geometry and combinatorial part, algebra, and then representation. So that's the menu for today's talk. So let's start with the Donaldson-Thomas invariants. And this is actually a very notoriously difficult subject. And if you want to understand it mathematically, even the definition of the Donaldson-Thomas invariants, it's actually very hard to understand if you want to understand it precisely. But at least the rough idea is the follows. So here I have the geometry. It's a Carabel seaport. So it's a complex scalar manifold, and canonical class is trivial. And then, so given this geometry, there is an associated concept of derived category of bounded coherent sieves, so-called. So, okay, so what this is requires some explanation, and I'm not going to really explain it. But there is some category involved. And in this category, okay, so this is a little bit abstract thing. But if you like, you can regard this as just a fancy version of the cohomology. So if given a Carabel, you can consider cohomology in the values. And so this category information is a little bit refined information of this cohomology. So there is, you can, given an element on this category, there is associated element of the cohomology. So in physicists, it's called the charge of the d-branes. And then, okay, so we're going to count these sheaves. So these are like a sheaves, and we're going to count sieves, but not all the sieves. And that's where the stability condition comes in. And there is a formalism for discussing that. That's, well, if you given a word, it's called a Bridgeland stability condition. So you specify some something called as a stability condition. And given a stability condition, you can discuss whether the bundle is stable or not. And you're going to count only the stable ones. So, and then that's going to be the Donaldson-Thomas invariant. In physics language, this theta is like the Fi Iliopoulos parameter. So some parameter, and in fact, the counting depends on this parameter theta. Although I'm not going to really discuss too much about the theta depends today. So okay, so whatever it is, so we have a geometry itself and the data of the cohomology. If you like a physics terminology, you specify what is the charges of the d-branes. But there are various different types of d-branes that in different cycles having the same charge, or different type of sieves having the same element of the cohomology. And then you choose the parameter theta and then choose the stable ones. And that defines the moduli space. So this is the moduli space. Moduli space S. S means a stable. Moduli space of stable sheaves. And then you're going to define some number out of it. So moduli space itself is just a geometry. And you need to, in order to extract it, there is some definition. So basically, it's like a counting the number of points there. And then that is encapsulated in the concept so-called virtual fundamental class. So there is some virtual fundamental class, which takes values in the Chow group of the variety, and then you integrate integrate one, the number over that, and that defines an invariant, and that is known as the Donaldson-Thomas invariant. So that involves a complicated definition, but roughly speaking, it's almost like it's the moral of the. Okay, so this requires a careful explanation, but roughly speaking, it's like an Euler character, this moduli space. There is a moduli space, and you can take the Euler character to define the invariant. Or if you like, it's a BPS index in physics language. And except that this space is sometimes more complicated space. It's not necessarily a variety, etc. So for that reason, this requires a more careful explanation. But it's a number of BPS states, if you like, or the Euler character of the moduli space of stable sieves. And if you consider the generating function, so this is determined for each gamma element of the cohomology. And so in general, which means that there are in general different infinite number of such invariants. depending on, because there are infinite different choices of the gamma. And then for each of these things, you prepare a formal parameter and then consider the generating function of that, such that you have a single function with respect to this. So this is a single function, and you can expand the single function with respect to this formal parameter variable q, and you get a series of Donaldson-Thomas invariants. That's how the structure goes. And okay, so why is this interesting? Well, it's some invariant of the sheaves on the Calabi manifold. And one interest comes from the fact that it's related to so-called Gromov-Witten invariance. So in some cases, it's related to the Gromov-Witten invariance, which is another enumerative invariance defined in a rather different ways. So there is some connection to other enumerative invariants, which many mathematicians have been interested in, connection to mirror symmetry and topological strings. So that's one of the motivations for studying these invariants. Okay, so now the point is that we just have a set of numbers which we summed up into a single function, single generating function. Now, so this itself in principle can be defined for any Calabi threefold. But here in this talk, I'm going to specialize to special class of manifolds called the toric Calabi threefold. And the beauty of the toric geometry is that there is an underlying combinatorics behind it, like a convex polytope, and all the information about the geometry are encoded in this combinatorics. So things are very concrete. And in practice, you just draw a two-dimensional, okay, so this is a two-dimensional lattice, Z2, and draw a convex polygon. Any convex polygon, and that actually defines a toric Calabi 3 in the sense I'm going to define. If you know a little bit more toric geometry, you can just consider it's as a section of a cone splitting in the third direction. And this cone you regard as the top dimensional cone of a so-called fan, from which you can define the toric Calabi threefold. But for the moment, it's just a combinatorics. It specifies the geometry itself. Now, in this case, the nice thing is that the toric geometry means that there is a cubic action of the torus, and then hence the torus action on the moduli space itself, and then we can count the fixed point. So this is the statement of equivalent localization, and then the non-trivial statement is that this fixed point set is one-to-one correspondence with the configuration of crystal, which we call the molten crystals. I'm going to define this momentarily, but that's how the counting comes into this geometrical discussion. So the geometry is like Euler character moduli space, but because of this equivalent localization, you have a sum of fixed point, which is the crystal. Now, what is the partition function in general? Well, partition function sometimes takes a very suggestive form. So these are some examples of the partition function which people found. So the simplest example, the Calabi 3, which is C3, the partition function takes a Markov function, which is this form, which is a beautiful infinite product form, Q to n, but the power is also n. And then there are other similar infinite product form in this thing. And then, in fact, this requires a non-trivial analysis. So people first, mathematicians define the invariant and compute the invariance one by one and constructed the generating series. Now, that itself is a formal series. You have no idea whether it becomes an infinite product form or not, but somewhat miraculously, there is an infinite product form, and you can prove that the partition function defined by the sum can be rewritten as this infinite product form, which is really a combinatorial miracle, kind of. And that was known already 10 years ago, in fact, more than 10 years ago, when I started working on this. In fact, almost 15 years ago. But the fact that such a beautiful formula exists requires some explanation. And why there is such a nice infinite product form? That was the question. Now, I'm partly a physicist, so I have some physics explanation of why there's infinite product form using the connection of strings invoking dualities in M series and string theory, which explains this thing. Which was very good. But on the other hand, if you take a more mathematical viewpoint, quite often when you have some infinite product form like this, that means that there is a nice structure behind it. And in particular, quite often these things appear as a character of some algebra. And it's not actually too hard to imagine that. For example, here you have q to n, right? So to the power n, etc., which means that probably there is some generator. So the algebra generated by generator relations. And suppose that there is a generator correspond to q to n, like some generator with weight n. And there may be n copies of that because n to the power. And then, okay, it's simply infinite product form. There are actually no relations. So it's almost a free algebra, freely generated algebra. And it turns out that algebra was already known in the literature, and more or less, it's called a W1 plus infinity algebra, or more in the physics-friendly notation, it's known as a free boson, free fermion. It's a free theory. So, in fact, in statistical mechanics, you might encounter some nice infinite product partition function for free series, and that's the same as here. Yeah, so this is reminiscent of many of the character formulas. And so it's natural to imagine that there is some algebra. Even in these cases, there should be some underlying algebra behind. But back then, I thought about that, but there was no obvious answer, partly because some details of what type of algebras to expect and the representation theory, that was not known back then. Well, by hindsight, you can almost cook up something from here, and that turns out to be more or less correct answer. But that was not known. So that's how I came into the business of what is the underlying algebra behind. And if there's an algebra, perhaps the combinatorial structure we face can be regarded as a representation. In mathematics, if you have algebra, there is a natural concept of representation. So it's natural to imagine that there is some infinite dimensional algebra, and if you consider representation of that, you get the crystal from that. Now, that is a mathematical discussion, but there is also a physics motivation for that. So some physicists, including Harvey and Moore, conjecture that this comes from some supersymmetric gauge theory, and in supersymmetric gauge theory, there might be a concept of algebra. People call it the BPS state algebra, and that BPS state algebra might be exactly this algebra. And the precise definition of that is not important, but basically, like you take particles and then consider the scattering of these particles and then define a product out of that, or something like that. And so that's not necessarily the most precise way, but people somehow expect also physics-wise that there are some nice algebras underlying that. And so we're going to discuss what algebra it could be. That's going to be the question. Okay, if there are any questions, let me know. Yes, but otherwise I'll proceed. Now, in order to discuss this, we need to take a slightly different viewpoint from the Calabi-Yau geometry itself, and that is the viewpoint of the quiver. Quiver with potential. In math, it's called a quiver with potential or superpotential in physics language. And this is very simple in a sense. So quiver is something you already know more or less. So it's just an oriented graph. If you like, you can impose the finiteness condition, etc. But it's sort of obvious. It's just a set of vertices and arrows connecting between them. Just oriented graph, nothing complicated. Now there is a concept of potential, and potential. Okay, so it involves the closed path. So on the oriented graph, you can go around the vertices following the arrows. Well, arrows are oriented, so you cannot go against the orientation of the arrow. You just follow it, and then you come back, and that defines the closed path. And the superpotential is a formal sum of this closed path. Well, in physics, it's often called the trace of the closed path, and then consider the sum. That's not the superpotential. Now, so that's the formal sum of the closed path, just the sum of closed paths. And then once you have this data, quiver with potential, then there's a nice algebra called quiver path algebra, which says that, okay, so whenever there is a closed path, you can formally define the derivative with respect to one of the arrows. So, okay, there is a blackboard, so in fact, I'm tempted to use it. So, for example, there are like 3 arrows going x, y, z. And then superpotential might contain x, y, z. And then there is a concept of taking a derivative of this with respect to, or maybe it's too low. You can take a derivative of this with respect to x. Oh, okay, maybe it's, and then, okay, so you can imagine that it's natural to define this to be y times z. So this is a cycle, you're going to interpret it cyclically. So, given this formal sum, you can define some formal derivatives, and then you consider the ideals generated by the derivatives inside the algebra. So what is this algebra? This itself is an algebra generated by all the possible paths. And it's called algebra because you can consider the product when there are two paths, and if they can concatenate, you just concatenate that you define to be a product. If no, you can just define the product to be 0. So it's called a path algebra, and then there is a relation. This is called a Jacobian ideal, and so this is the concept of Quiver path algebra. Basically, the set of paths modulo relations, and now this itself is known to. Okay, well, suddenly, so now I need to make contact with the Calabi-Yau geometry. So Calabi-Yau geometry itself is a geometry. I was talking about the quiver suddenly. So these are a priori completely different data. But there is a sense that there is a relation between this geometry and the quiver data. And there are several different ways of formulating it. One way which actually I kind of like because I worked on it when I was a grad student is that I was talking about the counting stable objects here in the coherent sieve. So this is like a vector bundles. But there is the statement is that given the toric Calabi-Yau 3, there exists some quiver with potential such that the left-hand side can be formulated at this module category on the right-hand side. And here, the module category means basically consider representations. So this path algebra itself is abstractly just a set of arrows. And so far, it's just abstractly, it's a mathematical concept. But if you can consider module category of that, which in practice means that each arrow is now represented by concrete matrices between final dimensional vector spaces associated with the vertices. So, so that's like a considering representation, and that's formally known as a module. And then there is a little bit of a going to derived category involved there. But there is something which captures the original information. So that's a non-trivial statement, but at least in many cases, it's known to be true. Non-abelian quiver. Yeah, it is a non-abelian. Well, let's see. Yes. Well, let's see. Well, moduli space. Let's see. Well, let's see. In a sense, the non-abelian nature, you mean the non-abelian in the quiver node, right? So yes. Yes. Yeah, but that's also contained in this space. So in other words, this itself is a space, original space. But we consider not only for example, if you consider a point-like object in the space, then the moduli space of that is the space itself, because the point moves around the space. But now, in addition, I consider, for example, sub-dimension, sub-variety inside it, then consider moduli space, which encodes more information than the geometry itself. Yes. Yeah, nodes correspond vector spaces. Yes. And then that's in general not rank 1, so it's no abelian nodes. Yes, no abelian nodes, and that corresponds to the fact that we consider not just like a point-like object, but more like a D0 to D2, D4, if you like. Yes. Yeah, and in a sense, that's somewhat more natural from this viewpoint. Yes. And one of the reasons is that, well, partly because we want to consider all the possible D-brane charges in the physics language. So we want to consider all the possible charges. So we want to consider D0, D4, D2, everything. And if you consider all, then the lengths of the quivers are going to be completely general.
I guess it's like what comes from equals chicken because if it's possible for you to have the relations are very specific. You only talk about variables that are not being used. So there are many distinctions.
Yes, yes. Yes, yes. Yes, that's right. That's right. So it's you consider more general thing. So in a sense, this itself is relatively, in that sense, a large information. So it contains the original geometry, and also as well as the symmetric product, but way more are also contained in all these geometry. And in a sense, philosophy is to consider all the possible such things together. And okay, so that's related to the fact that people often talk about, let's see, there is a sense that this the whole package, so it's a little bit of a gigantic thing, but people found in the algebraic geometry that it's actually useful to talk about the whole space and whole set of this derived category. And that's a huge thing, but that contains reasonably strong information about the original space itself, from which you can almost recover, not completely, but almost recover the original geometry, yes. And for that, it's useful to consider such things, yes. Yes, and so, and then the thing is that, so this itself is the, okay, so this itself counts the so-called top, this itself doesn't impose a stability condition. So there was a parameter theta in my definition of the geometric invariant. But here in this discussion, basically people are interested in topological type of the objects. So they are not interested whether they are stable or not. Okay, well, I forgot to say the stable is not too different from the stable stability you might imagine in physics-wise, if the particle is stable. For example, if the particle decays, it's called unstable. And so whether the particle is stable or not, that's the stability condition. And the stability condition I was talking about is a mathematical incarnation of that. It's almost like if the mass of the particle, when it's split into that, if the single particle is split into two, and if the mass of the resulting two particle is larger than that of the original particle, the decay doesn't happen because it's kinematically forbidden. So that's something we encounter in physics and all the time. And there is a similar concept, some mathematical incarnation of that, which is also called a stability condition for good reason. And so, but of course, that depends on what is the mass of the particle, which is a parameter. So even if you specify what is the, so this is like a charges, right? So even if you specify a charge of a particle, the mass can be different depending on the parameters. And that's so that's a stability condition I'm talking about in a physics sense. Now, you can also discuss, in addition to that, you can enrich this information by such consideration of stable objects. And if you consider only the stable objects only, you can go, that gives the Donaldson-Thomas invariant. So you can formulate the Donaldson-Thomas invariant on this way, on the left-hand side, which is the original definition by Donaldson-Thomas. In fact, it was Thomas, I guess. Donaldson was his advisor. And but also, because of this thing, you might hope to formulate this purely in Quiver language. So once you realize that, so it was a little bit roundabout way, but in a sense, in the end, the end result is that you can just talk about a quiver with potential, and everything should be able to formulate such that things become simple. And so that's how you come to quiver and potential. Well, of course, the question is that given the Calabi geometry, what is the quiver and potential? That's a concrete question, and there are some algorithm for constructing such pairs given a Tori Calabi 3. But I don't need a general version. But for example, here, this is the one. The simplest one is the quiver one node with 3 arrows with potential x, y, z, and x, z, y. So this is not commutative, so you need to remember the orientations. And if you take a derivative of this with respect to x, you get the relation like, okay, with respect to z, for example, you get the relation like xy equal yx. So you need to think cyclically. So you can cyclically permute the variables inside. It's like inside a trace. So you get 3 variables, and then they commute with each other, which really reproduce a C3. If you like, in the algebraic geometry language, it's a spec of C3. So that's how you get the geometry C3. Now, this example is more interesting. So you have 4 arrows, 2 nodes, 4 arrows, and then there's a product. It's almost the same, but the indices are different. 1, 1, 2, 2, 1, 2, 1, 1, 2, 1. Indices are a little bit different. If you take a derivative, you get some expression. But in this case, it's this thing is quadratic. So if derivative involves a cubic relation. So some relation is generated, but it doesn't mean that they commute with each other. But there is a more non-commutative relation. In fact, for that reason, this is discussed as a non-commutative resolution in some math literature. So there is some non-commutative algebra generated by this, which captures some information of the original geometry. And then it turns out the geometry itself is known as a conifold. So I forgot to say that this is in complex coordinate, this is an equation like xy equals zw, where xy, zw are all complex coordinates. So 4 complex coordinates, 1 relation, so you get like 3-fold. Yeah, so this is the concrete example of Quiver and potential. So once you know in some method that these pairs correspond to geometries, we can just forget about the geometry and keep pushing this. Now, what type of data you can do, and that's the beauty of this so-called brain tiling story comes in. And one little bit unsatisfactory aspect of this is that I keep saying that the quiver and the potential. So of course it's fine, but these are very different data. But there is a way to package everything into something simple, and that is this idea of drawing the quiver on a two-dimensional torus. So here it's the simplest example. That was the same example, one node and three arrows. And previously, I need to remember that this W is XYZ minus XZW, which is extra data in addition to the quiver. And but suppose that the quiver is written on a two-dimensional torus like this. So here it's a torus. So this above and below, and then the left and right, they are each identified. So you get a two-dimensional torus when you glue them together. And there are three arrows. But now these are not, previously it was an abstract graph. But here now it's realized very concretely on the two-dimensional torus. And in particular, you can talk about faces. Now the faces exist. And you look at the faces. In this example, if you go around the faces, XYZ and XZY, and XZY and XYZ. And if you go around the face, you get the product of these. And in fact, they are in opposite orientation. There are two small triangles here, but they are in opposite orientation if you go around the path. So you get, and if you remember that as a sign convention, then you get this constraint. So this is a reincarnation of this superpotential data. And in this language, it's actually very nice. So originally, we have vertices and arrows, but also we now have the information faces. Faces correspond to the information of the potential or relation of the path algebra. So things are packaged in a very nice way. Okay, so there are more complicated examples, which I'm not going to explain, but you can keep repeating that. Now, so this was the quiver with relations, and now I can talk about the Quiver Yangian itself, which is the infinite dimensional algebra. So, okay, so it's actually easy to write down the algebra itself now that you understand it. So this was the same quiver, which I discussed before. So let's say two examples. So in order to write down the algebra, I need a little bit of preparations. And the preparation is to prepare a variable, which I called h, to each of the edges, each of the arrows. For each of the arrows, I write down the variable. So in this case, there are three arrows, three variables. In this case, four arrows. You just prepare four variables. Now, but there is some constraint. The constraint is that whenever there is a term like xyz or xyzy appears, the sum of these variables should sum up to 0. It should be 0. So xyz, so which means that if you write down the corresponding parameters, x1 plus x2 plus x3, they should be 0. Yes, but it's similar to the so-called flavor charge. Yes, the flavor charge. Yeah, indeed, it's like in physics language. These are multiplets, chiral fields, chiral multiplets, and you assign some charges to each of the x, y, z, and then this superpotential should be invariant under the. It should be invariant on the flavor symmetry, which means the sum of the charges should be 0. Yes, this is just a roundabout way of saying that. And in this case, there are two terms, but these are the same terms. It's just orders are different, so it just keeps like the same relation. So three variables with one relation, leaving two parameters, for example. And that's how you get. So these are the flavor charges. Now the R symmetry you mentioned is the one where W is not do not have charge 0, but rather charge +2. It's a number. So if you want to you're interested in that, you should look for something with the instead of 0, your sum is 2, and that will play an important role soon, in fact. Yeah, so and then you can do something similar here. So again, here in this example, there are four fields, and for each arrows or fields, you associate some variables, and then in this case, again, it's the same term, so the sum is 0. So this is something I think anybody can understand. You just impose some condition. You prepare some variables and impose some linear relations. Yeah, these are sometimes called equivalent parameters, and related with the. I was talking about the equivalent localization and etc. And it's somewhat related with that. But You can just think of it as a parameter. And now, now given this, so you can already write down the Quiver Yangian. And the way to do that is to first, algebra is written down by first writing by generators and the relations. And then the generators are of this form. So first of all, this index A, which is the index for the vertex of the quiver. For each vertex of the quiver, for example, in this example, it's just one vertex, so just one copy. So you can essentially forget about this upper index. But there can be example where, in this case, there are 3 vertices. In this case, there are 3 copies of the same thing. And each of these things, it depends on the parameter z. It's in integral model jargon, it's called a spectral parameter, but it's just a formal parameter. And so in particular, you can expand with this parameter, and there you get infinitely many such things. So there's a little bit of subtlety of whether there's a psi starts from infinity to, or some, you can truncate it to some finite number. But E and F starts from the 0 to infinity. Anyway, that's important in practice, but not probably important for this particular talk. So there is a EF psi. And this EF psi plays a role very similar to EF psi or EFH probably in the SL2. So if you know the representation of SL2, or like in the quantum mechanics language, like a J plus minus and J3. In the quantum mechanics, there is a Cartan. So this plays a role of the Cartan, and this plays a role of raising lowering operators, or creation annihilation operators. So it's just a fancy version of that. So it's like there is SL2 for each vertex of the quiver, which actually happens. For example, you might know that the algebra SL3, SL4, they're like copies of SL2 intertwined with each other. It's very similar. But the normal feature is that depends on the spectral parameter. So it packages infinite set of generators into single thing. So we have a copy of the, we call it the Shubari generator, some set of generators, EF psi, for each of the vertex of the quiver. And basically, you can write down this relation. So this relation, which is a horrible relation, but let me try to explain a little bit, yes. And in fact, it is horrible, in fact, and that's, in fact, people discuss these type of relations already, certainly before us, and people call it the quantum toroidal algebra, or Dingui-Ohara algebra, or many different names have been attached to this. It's a complex thing, but let's see, it's not as bad as it means. So first of all, there are some signs, for example. You might care about some signs, plus, minus, and this basically says it's a Z2 grading. So it's like a super Lie algebra, bosons or fermions, and so this grading is determined when there is an arrow coming back and starting and coming back to the same vertex, you call it a boson with the Z2 grading 0. But otherwise, it's 1. And it actually has an intuitive meaning. So if you get bored, right? So if it's a boson, you can keep doing it because it's a boson. And then that's related to the fact that there is a arrow coming and going back. So if there is a vertex starting and coming back to yourself, you can keep going around forever. And that awfully sounds like the fact that the vertex has a bosonic structure. Whereas if there's no such arrow, you cannot really do that. So you are lonely, so you stop there. It sounds like a fermion. So that's this Z2 grading. Anyway, it's a little bit of technicality, not the most important thing. So there is a plus minus sign, and it determines the kind of bosonic fermionic character of the story. But let's see, what are these? Well, these are, okay, so these are relations, and then there are sometimes equivalent modulo something. So, but these means that these are each of these things. For example, let's look at this relation, and psi times psi. Each of these is a formal power series in Z and W. So you can expand both in Z and W on both left-hand side and right-hand side, and you get the formal series. And then all those relations see is that some of the terms, many of the terms, you actually don't care. For example, in the first case, if the power of W is positive, so there, if you expand the Z and W, you get the power of Z and W, both negative and positive powers. But what it says is that if W has a positive power, you don't care about it. So the left-hand side and right-hand side don't need too much. But there are some finite number of singular terms with a W negative power, and those should match. And that is what is meant here. So it's roughly speaking, the singular terms match. So you might remember that D and W has this power series expansion with the 1 over z, etc. And a singular part of this should match. And then, well, that is known, that type of thing is known in conformal field theory. So in conformal field theory, there's something similar, or vertex operator algebra in mathematical jargon, you have something similar, you have something which depends on the parameter, and equivalence is up to non-singular terms. And this has a similar structure to what you find in conformal field theory. And then the final ingredient, which is very important, is that this function, which is called the bar phi, and I forgot to write that delta is z minus w. So it's a difference of z and w. And then that's also something determines, first of all, it's a rational function. And another thing is that it's determined from the Quiver data. So these are the parameters with associated h, and for each h or arrow starting from b to a, there is this factor, or the other way around, numerator, denominator. So it's some concrete, very concrete rational function determined from the Quiver data, and there are many more relations. This is an anti-commutator or commutator depending on the grading, etc. But it's this relation. In fact, you can expand with this to the modes. Modes means so you can expand it to z and w and write down these relations, but they look horrible. So this is the only way I can understand it. Yes. Well, let's see. Well, in these discussions, in this discussion, I tend to think about the UN, for example. Yes. So. Well, let's see. Relation between global charges. Well, not exactly. So yeah. So the charges is the charges etc. are information of the So that's there is extra data like a spectral parameter dependence and an expansion of that. So, but of course there is some data. For example, you have a product of E, for example, and once you have a product of E, that's like applying creation operator to the vacuum, and that creates states with more charges, for example. Yes. Yeah, the state itself, yes. So right, so that's now so far I introduced only the algebra very, very abstractly. And so far the connection to what I have been describing before is not at all clear. But the bottom line is that if you can consider the representation of this in terms of the crystal melting, which means that each state in the representation, which is like which is applying this creation operator E to the vacuum, to the vacuum itself is the BPS state. So what it means the follows. So BPS state is some state with a BPS charge, right? So charges, so it's like electromagnetic fields, but it's a more complicated electromagnetism. So there are many copies of electromagnetism. So electromagnetism 1, electromagnetism 2. So the charge is not a single number, but it's like a vector. Now, for example, if there is suppose that it has charge 2, 2, for example, for two different U1s. Now, you might imagine that you can decompose that into 2, 1, and then bringing in something with a 0, 1. The charge should be preserved. So you might expect that if it's a 2, 2, you can create it by starting with the vacuum and applying 0, 1 twice, 1, 0 twice, for example. And that means that 2, 2 state is created by four creation operators with two different types. And that is and this E is such a creation operator. In other words, this creation operator is a very physical operation, bringing an atom with specific charge from infinity. So there is some crystal here with some specific charge. And I want to make a bound state with one more charge. And what I'm going to do is to bring a particle with some charge from very, very far away, and then bring it all the way to in a very close proximity to the original crystal, such that you have a charge with a large state, bound state with a larger charge. So that is the physical meaning. And well, let's see. Well, it's basically mesons, I would say. Yes. Yeah. That's partly because each of these things represents the element of the path algebra, and which is like a concatenation of the path. So you start with the path and going around. Yes. So, but it's almost like a mesons, but it's not this. Mesons usually closed path, right? So, but here you don't necessarily consider closed path. It's open path more like. Well, it's but the baryon, well, maybe it depends on the terminology, but for me, baryon is like a contract with the epsilon tensor, but yes.
So if it's U1, then probably it's baryon.
Yes. To me, baryon is like a dibaryon, what you might call it, like a contracted epsilon tensor. But yes, but it's open path. It's element of the chiral ring, if you like. Yes, and that's. Yes. Yes. Yeah, that's right. So these are really the physical. Yeah. So in the quantum mechanics, there are various different viewpoints. So the viewpoint when I'm talking about the particles, etc., I have in mind like a quantum mechanics picture, and then there are the BPS particles inside it, which has electromagnetic charges. So that was the picture I have. But of course, you can go back to more like a 4D, Quiver quantum mechanics description, and then there, these particles I'm talking about are like a product of fields, really like a bound set of fields, yes. And that's so. In fact, that's more or less the general strategies, general philosophy here. That it looks very complicated, but in a sense, the idea is that the statement that although there are BPS states or some states contribute to the index, and or to Donaldson-Thomas invariant, and they can be decomposed into something basic ingredients, which we call the atoms. So if you turn the argument around, if you start with the atoms, you can construct a representation or construct a more general state. And this generator, Lezing creation operator, is just to bring one atom from far away to combine to the rest. So that's the intuitive picture. And then this algebra is the algebraic translation of that. So there are some interesting issues. For example, there is a relation between E and E. They don't quite commute. E and EB, they don't quite commute. So there are particles of type A and particles type B. You can bring them together in a different order, and the answer is different. And that is familiar in the electromagnetism. So if there are these electrons, so if there is mutually no local people call, like electrons and what is called, magnetic monopole, for example, then there is angular momentum in between, actually. So if you bring it in a different order, you get a different answer. So that type of mutual non-locality is reflected in the existence of this space phi. So it's some fancy version of electromagnetism in the physics language. Yeah, so that's a little bit more meanings. And then, so yeah, let's see. So that's algebra, and interestingly, mathematicians also thought about this type of algebra, but not completely. If you take this part generated by E only, so that's an algebra generated by creation operators. Mathematicians discussed it, and that's called a cohomological Hall algebra. And motivation is not too different to math, but and then what we have is that the similar structure, but with we have extended the structure both creation and annihilation operators, and then combined it together nicely. Now, I should come to the representation theory part. And yeah, so the basic idea was already discussed. But let's see. So now, in order to connect this story of the algebra back into the counting problems I started before, I'm going to consider representations. And then there is a nice combinatorial structure. So okay, so perhaps I can discuss this example. For the C3 example, the combinatorics which appear is this three-dimensional partitions. So hopefully there is a more formal definition, but the picture explains everything. Hopefully it's a three-dimensional picture. So it's like there is a corner, empty corner, and they keep taking both boxes from there. And in this case, it's obvious, but there is a nice way to reformulate in terms of the quiver. Yeah, so for example, one fancy way is to, well, let's see. So you can think of this edge box as a polynomial in x, y, z. So here there are three different directions, x, y, z. So if there's a position I, so for example, 0, 1, 0, 0, 1, it means that there's a variable z to power. 0, 0, 2, it means z squared. Or 1, 1, it's x, y, or each of these boxes corresponds to some monomials, right? So, and then what is the characterization of that, the thing that this is a 3D partition? Well, you can see it in the figures, but if you want a more fancy way, it means that this thing, if you consider complement of this finite set, it actually is an idea of the path algebra. That's a fancy way of saying that. The explanation of that is that path algebra means, in this case, remember there are three variables, x, y, z, because it's just C3, and they commute with each other. And path algebra, you're going to consider representation of the path algebra, which means that you just multiply by x, y, z. So, and the fact that it defines idea means that if you're in the complement of this thing, and then go in one of the three different directions, you're still in the complement. So that can be deformed as a condition that there is an ideal in this path algebra. And so now that I'm not going into detail, but that more or less explains the concept. So here, given a general quiver with potentials, you can define the set of atoms. Okay, so you can define some structure like this. Here, in this case, only x, y, z, and you just go along the arrows, and then you get the structure. And then, of course, you need to remember x, y equal to y, x. So sometimes they arrive at the same point because they are relations. And the idea is very similar. Even if you have more complicated quiver, you can just follow along the arrows, and then sometimes they are the same, and when they're the same, you declare to be the same point. And in this case, there are three different directions, which is kind of obvious because x, y, z. In general, it's more complicated. It's less obvious, but there are three parameters you can think of because there is a toric cardinal 3. Or, in fact, the two parameters correspond to the Flavor symmetry, one for the R symmetry, which you mentioned, yes. So the statement is that you can consider a set of arrows on the quiver, choose some particular vertex, consider a set of arrows, and then consider that with modular relations, and then you get some combinatorial structure. And if you consider taking finite set like this, which satisfies some combinatorial relations, and then you can let the arrows, in this case x, y, z, but in general more general variables, to act on this space. That's how you get the representations. And it's a roundabout way. So how to do that thing happens. It's a complicated combinatorics, and when I always try to explain it, I lose people. But at least this is one example of how you get the crystal, and it looks awfully complicated. But it's actually not, because here in this case it's a complicated quiver. But then I have chosen this, so you can go around and sometimes come back. And then in this picture, sometimes when you come back, you actually go deeper in the crystal. But you keep going around, and there are some relations, and then there is a natural structure which emerges, and then if you draw this, you get this three-dimensional structure, and then that's how the crystal works. And almost by definition, the arrows act on this three-dimensional crystal. And just like in this example, you take a point, and then there is action of x, which is to just shift in one direction. And there is a generalization of the statement to completely general quivers, at least those associated with toric cardinal 3, and that defines the combinatorial structure. And now, what I said so far is that there is arrows act. Arrows of path algebra act. But in fact, that action can be promoted to action of the algebra too. So I defined the action Quiver Yangian, which is EF psi. And then, so here is the finite set, which I call the crystal, which is like a counterpart of the 3D partitions. And there is some actions. You can let some action of that. And in fact, this is somewhat similar to what you might expect. So this is a psi plays a role of the Cartan, so it actually doesn't do much, just a coefficient. Here, this thing is a creation operator. So you can add one of the atoms to the crystal. So it's a 3D partition with n atoms. You can add one atoms. And there are typically different ways of putting the atoms. So you have to sum over them. And then there's a little bit of weight, which is complicated with some parameter z dependent, etc. But you search for the, this is basically the ansatz. And f is an annihilation operator. So instead of adding it, you remove some atoms. Now, in general, there are multiple nodes. So there is index A, which means that you're going to remove the atoms only associated with some particular vertex of the quiver. Yeah, so that's the one aspect. In general, there are multiple nodes. So when you go around the quiver like crazy, there are only three possibilities. You either land on this vertex or that vertex or that vertex. So you land on one of the three, right? So you start with there going around and you land on one of the vertex. And depending on where you land on, you associate three different colors, and that's how you get the three different colors in this crystal. So So that's the, and then there are three, so then correspondingly, when you remove other atoms, you can remove the atoms or of that color only. And so this is the how you get the representations. And then so once you know have some ansatz, you can try to choose this. So this E and F, some expressions, and you can cook up some expression for E and F such that this becomes the honest representation of the original algebra I was talking about. Now, in the original algebra, you might remember that there was some factor called this function, which is bar phi, which explains the like a mutual non-locality of the different particles in a sense, and or whatever appears here, and that thing is should appear in some representation, and indeed the answer is true. So this thing psi, capital psi, is a product of bar phi, and bar phi was the thing I defined previously, which appears in the algebra. So this data enters in a somewhat complicated way here, but this is how we get. And it's a product form, well, which is roughly speaking, it's a product form. If you push that electromagnetism further, what this means is that when you try to bring, so suppose that there's a crystal with a lot of electromagnetic particles, and if you try to bring in extra electromagnetic particles, then you're going to get well, kind of angular momentum. But what type of angular momentum? There is a, you can just take each atoms which already, each particle which already exists in the bound state. Consider the pair of new particle with that particle, and then just sum over all possible particle in the original bound state. So angular momentum is the sum of the angular momentum in a sense. And so that type of structure appears in this expression. And other things are, you can more or less try to cook things up. And that's how you get the representation. Yeah, so that's more or less what I wanted to say. So in the story we have, let's see. So okay, I don't really need this. So yeah. So what is the general lesson? So well, it's a nice example of the interplay between the algebras and geometries, the representations, and also physics. So in the original way I formulated it as some counting problem, abstract, but in a sense, it's a very traditional geometry of counting some invariants in the Calabi manifold. That's a geometry question. But through equivalent localization, you can consider that as a summation of crystal melting. But now we have the underlying algebra, and then this arises as a representation of that representation space for this algebra. And as I said, the physics meaning of that is that the BPS states are decomposed, each state in the BPS states is made from some more basic building blocks. And that basic building blocks is like atoms, which are called atoms in the crystal. And then you can define the creation annihilation operator by bringing particles from infinity. And so that's how you get the infinite dimensional algebra. And so that itself you can formulate also in the physics of quantum mechanics, but also in the more in the language of string theories and M theory and all that. So that's how the story goes. And so this shows that, and interestingly, this Quiver Yangian itself, that's the new algebraic structure we found. And surprisingly, not okay. So there are mathematical works on, okay, so I didn't say that what Yangian is, okay, I gave a definition, but Yangian is some integral model structure. So it's nice integral model structure, so-called. But the integral model structure have been studied by mathematicians and also physicists for a long, long time. But whenever there is a discussion, quite often there is underlying Lie algebra. But partly because it's integral models, etc., it means that there is a symmetry, and the symmetry should be a Lie algebra. So, and then you see Lie algebra, at least finite dimensional ones are classified. So that's how you get the Lie algebra quite often. But here in this discussion, you don't actually need, there is no underlying Lie algebra, but it's more like a quiver. And that makes sense because when you do the quiver quantum mechanics, etc., the underlying data is a quiver. So this probably suggests that the concept of symmetry is somewhat extended, needs to be extended. And you start with some physical setup with a defining data, which in this case is a quiver. And then there is underlying symmetry behind it, which will lead to through to interplay between geometries and representation theories and algebra mathematically. And that I suspect is a much more general lesson. Thank you.